Hello, ladies and gentlemen. Welcome to today's webinar about design of craneways according to Eurocode 1993 Part 6. My name is Wieland Götzler, and today I'm supported by my colleagues Steffen Klaus and Andreas Herold, who will help you with your questions. And if you have some questions during the webinar, you can easily use the chat function or question function in the webinar panel. Today's content is first, in the first part I will show you the features of the standalone program Craneway, followed by the design of a craneway according to Eurocode 3 Part 6. So first let's talk about the features of the Craneway program. Craneway is a standalone program, which means that it's completely independent from other programs like RFEM or RSTAB. You don't need to define different parts of the model. You just have to define the craneway itself, and this leads to a fast and comfortable modeling and design. You can use every eye section, like welded or rolled eye sections, and you can strengthen them by channel profiles or angles. You can define up to 3 cranes with a maximum of 20 crane axes. And one of the biggest advantages of the standalone module Craneway is that you can have an automatic combination of load cases for different design situations like fatigue, ultimate limit state, or serviceability limit state. The design is according to Eurocode 3 Part 6, which includes the stress design of the crane, fatigue, design of deformations, as well as the local buckling design and the lateral torsional buckling design according P-delta method or theory second order, including the warping of the cross-section. Another big benefit of Craneway is that you can have a presentation of the results in the graphic, like deformations, bending moments, as well as a full printout, which makes a provable static calculation of the craneway possible. Now we will just move on to the Craneway program itself. It might look quite similar to you if you are already using RSTAB or RFEM. So in the first step, I will just define a model. In this case, let's say I want to define Craneway webinar. And in the first mask, you have to define which material you want to use. I will just use a S355. But as you can see in the list and also on the link, you can use a material library, as you already might know from the other programs. You can define a new material if you don't find the correct one for your calculation. But in this case, I will just use the S355. You have a design possible according to DIN 4132 for Germany, and according to Eurocode 3 for the European Union design for several national annexes. And if your national annex is not available in the module, you can easily define a new one and change partial safety factors according to your needs. Today I want to define a bridge crane, and I want to define it according to SEN, which means that's the formulas and the variables which is included in the main standard and not in the national annex. In the next step, I want to define, or I have to define the geometry of the crane, of the craneway. As in the main view in RFEM or RSTAB, you can easily rotate, you can zoom in, zoom out as you wish, and check your structure. So I like to work in isometric view. I can use this one. And today we have an example like 28-meter craneway. And on the bottom I have to define the supports, we have a intermediate support at 40 meters length and at the end of the craneway at 28 meters. There are several standard types of supports like hinged movable as an intermediate support, and it will give you the automatic definition of the displacement and rotations, which is disabled at the moment. But if you want to define a full user-defined support, you can easily use user-defined, and you have access to all the degrees of freedom. You can also use just intermediate support on the upper flange, and you can check it in the graphic. In this example, we just have hinged movable like this, and we want to define a release in the middle of the craneway like this. In the next mask, you can also check the releases. If you define a user-defined release, you can also have the access to the other degrees of freedom over there to, for example, define a shear hinge or just a normal hinge as you wish. I will just use the standard hinge in this example. You can also use warping supports or hinges as stiff, or you can also define springs in the mask over there. And with the detailed dialog over there, you can also let the module calculate spring stiffness for warping. In this example, we want to keep it simple, so we don't take the warping into account. Let me just show you the stiffeners. The stiffeners over there, they are not for the calculation of the internal forces, but they will define the intermediate panels for the design of local buckling. So in this example, I want to have 6 intermediate panels on both sides as a regular, or you can even use user-defined and choose whatever distance you want. Okay, regular 6 panels, and that's okay with the definition of the craneway itself. We can just continue to the next dialog, which is cross sections. There, on the first step, you can choose between rolled or welded sections. Let me take a look at the rolled sections. You have a filter on the left side for several manufacturers and standard groups. That means you have quite a big library of possible eye sections, for example, ArcelorMittal or standard sections, British Steel, for example. In this example, I want to use a welded section, which is quite easy to define. You just have to define these dimensions over there, and the example is 1,200 millimeters high. 600 millimeters is the upper flange. 12 millimeters as the web. The width at the bottom is 320 millimeters thickness, and the welds both are 6 millimeters. Okay. The next is to define a rail section. You can both use a splice, like a flat bar on the upper flange. As you can see on the right, you can also take a look at the cross section over there. Define the splice, or in this example, I want to have a S75 section, like this one. Okay. On the bottom, you can define stabilizations or strengthening sections like angles on the flange, or rolled sections, which in this case is not possible for this section with a width of 600, but I can easily deactivate it and just continue with this one. On the right side, you can also see that you can take the aware of the rail section into account defined by the standard. As you can see, the section properties are modified automatically. You don't have to do anything. You get some info in the section of the rail. And in this case, I have elastic support under the rail, so I don't want to take the rail section into account for the section properties. I will just switch this checkbox off, and in the details dialog, in the middle of that, you can see that you can define the rail flange connection. In this case, as I said, I don't want to have to take it into account, the rail. That means, as I said, we have an elastomeric bearing pad with a height of 6 millimeters, which is fine. Okay. And with this definition, we can just switch to the next mask, which is the loading. So on the top of the loading mask, you can define how many cranes you want to design. On the craneway, in this example, it's just one. We have a girder buffer on both sides, and we want to define, or we want to design both girders. That means with maximum and minimum loading. Crane description. This is what you usually get with a for the static calculation. That means you have a crane you want to take into account, and this data sheet you will find all the loading, the name, and the S-class for this crane. For this example, I have a, let me take a look, 17 tons crane. The S-class is S5, and over there you can see the dynamic coefficients, which should be clearly visible in the data sheet of the crane. If the loads you have to define over there are already including the dynamic coefficients, or they are without. If they are without the dynamic coefficients, you have to define it over there. So in this example, I have to define it 1.1 as phi1 and 1.38 as the phi2. The rest is of the values, it's already okay, like this. And we have a crane buffer of 5 centimeters on both sides. That means the crane can run from this length to along the craneway. Yeah, you can already, you will see this in the graphic later. We have a crane axis of 4 in this example, and the distance between the crane axis is 2 meters, 5.6 and 2 meters. And the loading I have already prepared in a small Excel sheet. So I will just copy the loads from this sheet by selecting all the loads, selecting the cells, and Control V, paste the loads over there. We have a minimum load on the girder 2, because I want to design both girders. Yes. And we also have an additional skew force, minus 20.1. Okay. Now on the bottom you can see we have an increment of crane positions of 1 meter, and it means that we have 58 crane positions. And this leads to 291 load combinations. If you define, let's say, 10 centimeters, you get almost 2,000 load combinations, and this is basically up to you. Yeah, you have to get some design possible, but you also don't want to have a mesh like, let's say mesh, you also don't want to have an increment of crane positions like 5 meters to have only 10 crane positions. So in this example, I want to use 0.5 meters. Then I have 76 crane positions and 381 load combinations. And what does this mean? You can take a look in the graphic, 3D rendering over there, and there you can check the definition of the crane. We have 4 crane axes with these 2 meters over there, 5.6 and 2, and this is basically the calculation which is done later when you press the calculation button. The program will calculate all the load positions, load blocks and combinations according to Eurocode 3. When you just switch back and define a buffer of, let's say, 5 meters on the right side, check the rendering again, you can, let me take a look, load block 1 and 2. This is this one, yeah, you can see the distance that the crane, there's a distance of about 5 meters on this side. The loads are not appearing to be above the support over there. But on the left side, the loads will be above the support at the X location of about 0 meters. So you can check all the load combinations and all the crane positions in the graphic, like for the resistance, for fatigue, and for deformations. Let me just switch back to the crane buffer of 0.5 meters. This is also what you can use for the craneway if you have more than one crane and you don't want to, and you want to keep the distance between the cranes. You have to define the buffers. So in this mask, I think we are finished and we can take a look at the load combinations. This is more like an overview for you. So you can see that for the resistance, you have an amount of 381 load combinations with the partial safety factors, with the crane positions and so on. So if you imagine to do this manually, it will just be really time consuming to get all these load positions and to get all these combinations done. And in this case, it's a very big advantage, I would say. Let's take a look at the imperfections. Imperfections you can both define manually in the module, or the program Craneway will define it automatically for you according to buckling curve, and it will apply the imperfection according to Eurocode 3 automatically. So right now I can just run the design. Will take some time for the 381 load combinations. There are 2 ways of calculation implemented in this program. You have a fast calculation, which means that the design will run according first order theory first, and then the worst load combinations and design situations will be designed according P delta or second order theory calculation method, including the imperfections, including warping of the construction. So if you imagine to design all the design situations and all the combinations according to P delta, including imperfection and warping torsion, it will be even a lot more time consuming, and therefore we have a fast calculation and a detailed calculation. If there is a warning hint like there's insufficient number of eigenvalues, you get a warning hint, and in this case we want to increase the number of eigenvalues, of course. So this is the 12 design combinations we have. Of course, in this design situation 77, we have to design according P delta method, but it's less than the 381 before. now the calculation finished, and you get a design summary like in other additional modules. For example, SteelEC3, you get results as a design summary, internal forces, support forces, stress analysis, and so on. So in the first step, we want to take a look at the stress analysis, which is fulfilled by this criteria. We have a governing load combination 142, and you get a full stress design, for example, shear stresses, sigma Z, sigma X stresses up to the equivalent stress, which shows that the design is fulfilled. You can also take a look at the internal forces as well as the support reactions. And with the File Export Tables button, you can also export these support reactions, for example, to have them for further work, for example, in RFEM or RSTAB. You get also the plate buckling design, and which might be also interesting for you are the critical load factors for several load combinations. The module also gives you the opportunity to get the welding and fatigue design, and this is what I want to perform now. So I switched back to the cross-section mask and activate fatigue design as well as the weld design. So we define the weld thickness of 6 millimeters over there in the cross-section. And first we want to try to double as a double filled weld. And when you take a look at the detail categories, you get all the details for several stress points along the cross-section. You can also check the position of the detail category in the graphic. And when you click on calculation, you can see it's quite fast. It doesn't calculate the internal forces again. And you can see that it's quite overloaded. The fatigue design is about 400% now. And therefore I have to modify something. You can also take a look at the overloading detail like sigma X, and when you take a look over there, seems to be okay. But on the bottom you can see the sigma Z stresses, and this seems to be overloaded. So therefore I want to, over there you can see the sigma Z stress is overloaded, and therefore I have to improve something. What I can do now is I switch back to the cross-section dialog, and I will change the weld of the upper flange and the web over there. You can take a look at this graphic, and in this case I want to use butt welds. That means the web is fully welded through at this position. I just have to change the radio button over there. This was a small fault because it's still overloaded. I changed the type of the weld on the bottom, but I want to have it on the top of the web. Run the calculation again. And now you can see it's fine. Fatigue design over there. We can also take a look in the detail of the fatigue, and this seems to be okay now. You can check all the results in the graphics, but you can also take a look with the button graphics over there to have a view in the to have a bigger view in the program. You can also change the way of displaying the deformations, for example. This is a sigma stress, so first of all I want to change the deformations to U. Can increase the display factor just a bit, but this looks not very satisfying in this case, because just a line for deformations, it's not too useful, I would say. So in the display dialog over there, you have the results and you have deformations, members, and you can easily change to cross-sections colored. Reduce the scale just a bit, and there you can see that it's lateral torsional buckling. It looks like lateral torsional buckling. Deformation in this case, because I think it's the ultimate limit state, and this including the imperfection according to first eigenshape, which is, I think, the lateral torsional buckling. Okay. At the end of the calculation, the question is how you can send this to someone to prove the calculation, and therefore we will just create a new printout report. You have templates over there, and therefore I want to use the Crane girdle analysis as a template. Just open the printout report. As you can see, the printout at the moment it's still German, so easily just change the language to English. So even in this case, you can have a design according with the English language, and you can also change, let's say, to Italian, Spanish, or whatever you want to send the static calculation to a different country than you are working. Yeah. Okay. Like in Orphem or RSharp, you get the possibility to print graphics. This graphic of the crane is defined automatically to have an overview about the loads you've defined. But when you just close the printout report, save it, for example, I want to have this shape in the printout, you can easily just print it to report number 1. I only want to have the current one. Okay. And now you get the deformation of the craneway in the design combination 1. If you have some mistake, no problem. You can easily just click on the edit button and change, let's say, to the other side. Zoom in, click to go back to the printout report, and you have modified the graphic. All right. Let's save the printout. You can also use the mustprint function. Let's say you want to have you not want to have only the deformations for combination number 1. You want to have more combinations. It's no problem. You can use the printer button again, but change to mustprint settings. I want to have the results of, let's say, deformations combination 1, deformations combination 2, and let's say combination 27 of the current view. And you can see over there you get 3 graphics to the printout report. Window filling, this is okay. And now you get 3 more prints, yeah, for combination 2 as well as for combination 27. So you don't have to print each graphic again and again. You can easily print the internal forces, the deformations, just in one process. All right, let me just take a look at the questions you've sent to us. Yeah, all right. Sometimes we get the question to whether you have to find the skew force or the horizontal loads. So I just switch back to loading, and there you can see horizontal wheel loads as well for the max and min girdle, and you have the skew force. So this is basically dependent on the system. If you define both girdles, in my opinion, you should have the skew force only on the minimum girder with the minimum crane loads. If you design just one girder with this radio button, you can decide if you want to define the horizontal wheel loads or the skew force. Because if you design both, then it might be way too conservative, and yeah, you always want to have a economic design. So in this example, I've used both girders and the skew force on the girder with the minimum loads. So this is, we are pretty much at the, almost at the end of the presentation. So just let me give you some additional informations. What you can do after the webinar is you can easily just go to our webpage, dlubal.com, and there just move to downloads info, and you will find download trial version over there for all the main programs like RFEM, RSTAB, as well as the Craneway program. I would be very pleased if you just download it. Send us questions if you need some additional information. You can write us emails, you can call us at the phone number over there, and we are very happy to help you with your calculation. And I wish you good luck and a lot of fun with this program. Thank you very much for your attention.